Okay, so we're going to go over problem 3.31, which is the mountain lion jumping. So we're told that a running mountain lion can jump a distance, right, of 10 meters. I'm actually going to keep some colors going. So we know that it can jump 10 meters long and then also reach a height of 3 meters. Okay. Now, this lion, when it starts to jump, it's on the ground. And then when it falls back down from the jump, it's on the ground as well. And it's jumping like this. And the question that we have is, what is the speed that the mountain lion is able to jump with, right? What's the initial velocity of the mountain lion? Now, in order to go up and out, the velocity of the lion has to be going in some non-horizontal or vertical direction, but off at some angle. So the question, part A, is what is the speed of the mountain lion just as it leaves the ground? And then it says at what angle does it leave the ground. So the only way for this to go to the right and up, or out and up, is to jump with some velocity at non-90 degrees or non-0 degrees, okay? So our question is, what is this velocity and what is this angle, okay? So filling out the rest of this, right, our max height we get up here is 3 meters. And that's pretty much all the information that we're given. Right, a running mountain lion can leap 10 meters long, reaching a max height of 3. What is the speed? So it doesn't look like they gave us a whole ton, but let's start breaking things down. We know that we're dealing with motion in 2 dimensions. We're given delta x's and delta y's, so that tells us that we're dealing with kinematics. So we got delta x, v naught x, v naught y, or sorry, vfx. So I'm keeping red as the x. We have acceleration in the x direction, and then we have time, and I put time as blue because it is consistent, right? This mountain lion, at any one time, its x and y are tied to each other. Okay, so the t is what connects both of them in general when you're dealing with these types of problems. And then we have delta y, we have v naught y, we have v naught, or vf y. We have acceleration in the y direction, and again, time is there for both of them. So we can start filling in some information. We know that it's traveling 10 meters. We know that it goes a height of 3 meters. And something that we have to be consistent with is understanding when this mountain lion takes off from its initial position. We are dealing with as soon as it launches off, we are now in free fall, meaning the only force that is acting on the object is gravity. So our x acceleration is always going to be 0. There's no other force. After it lets go, there's no force in the x direction. After it stops touching the ground, there's no force in the x direction. But we know that we have gravity in the y direction. Okay, and our question is, right, what is this initial velocity? And a lot of the problems that we've done before is we were given the initial velocity and we had to break it into its components, right, the x component and the y component, and then we plug those into these problems. This is asking us to do things backwards, right, where we need to find the components and then add the components together to find this initial velocity and theta. So we're just doing a problem backwards. So when we're looking at this, we need to figure out a way for us to go forward in our problem solving, right? So looking at this, we have to, we're looking for v naught y and v naught x. So with our green information over here, I am one variable away from being able to solve. I want to find v naught y, and I know the displacement in the y direction, and I know ay is gravity. So we have to be able to figure out what more can I know about about our problem based on the information that we're given. So if I'm going to use a y of 3 meters, which refers to this point right here, we have to understand that that is the apex, that is the top of our parabolic motion. And in the y direction, what's happening there is we have lost our y velocity and we're starting to turn back around. So we were going in some positive y direction. Technically, we're going up, right? We're slowing down as we are going up. And then we reach some 0 point, and then we start to speed back up as we are going down. Okay, so at the top of our parabola, that is where we have an initial or a final velocity of 0. So I can break this motion in half for the sake of being able to identify a variable, right? So when the displacement of this line is 3 meters, when it reaches its top, it also has a final velocity of, at that moment, of 0, and it has an acceleration of -10. Okay, so with that information, I can now solve for the v naught y, and the equation that links those. Sorry, I don't know where my equation sheet went, but we need the equation that doesn't have t, so that is our vf squared is equal to v naught squared plus 2a delta x. So this helps find our v naught y, and I'm doing it in green to show that that's y. So if we rearrange this, we get vf squared minus 2a delta x is equal to v naught. I'm going to take the square root of that side. So if we plug in, I'm going to get the square root of vf squared, which is 0, right? So I'm going to get a -2, -10 times 3. So when we're looking at this, yeah, I understand that we have a minus 2a delta x over there underneath, but because it's -2 times -10, we get rid of that negative sign, which means that we are allowed to do that math, because you know if you have a negative under a square root, you cannot take it. But we have 2 times 10 times 3, and then we're going to take the square root of that. So we get 7.746 meters per second is our v naught y. Okay, so initially what we have is this green component of our initial velocity is 7.74 meters per second. Now, if we want to go and solve for v naught x, we have to know something about the time, right? That is our link between the two, because I cannot solve any equation right now. So we have to use our green information, our y information, to solve for the time, and then the time to solve for v naught x. So if we're thinking of an equation, because now we have all the information for the y except for t, so I'm going to do this one equation, delta y is equal to vft minus 1/2 at squared. So this is similar to our third equation, but instead of doing v naught t plus 1/2 at squared, when you use the final velocity, it turns into minus at squared. So you can look back at your equation card and see that. But we're still using the same information. We're saying delta x, or delta y is 3. We know that the v naught is 0, right? So I'm looking back at the green information. The v naught in the y direction is 0. So we're getting minus 1/2 -10 t squared. So we can solve for this. 3 divided by -1/2 divided by 10.6, and then we take the square root of it to get that. So the time it takes for the line to get to its apex is 0.7746 seconds. And then using this information, we can combine the time with our delta x. We could say delta x is equal to v naught t plus 1/2 at squared, where the acceleration in the x direction is 0. So I'm going to say that I know this thing. Oh yes, that's the other thing that we have to worry about. Right, so we solved for the time that it took to get to the half point right here. Okay, and the cool thing about parabolic motion, when you are starting from the ground and coming back to the ground, or starting from the same place that you ended, it's a parabola, right? So the time up is the same thing as the time down. So we found the half time, right? So this is the time to top of jump. So if I want to use the time to solve for delta x, I actually have to take double the time, right? So 2 times this, 2 times 0.7746 is the time back down to the ground, right? The time of total flight. Okay, and that ends up being 1 second, 1.549 seconds. So you have, like, when you're going between frames here, between information, you have to keep track of what you're looking at. So I can't just take the 0.7746 seconds, because that is not the time it takes to jump 10 meters, right? Our displacement in the x. Would it in theory be the time it takes to get to 5 meters? Absolutely. You just need to make sure the numbers you're working with make sense for the situation. So I cannot take that half time and say that that's the time it took to go 10 meters. So what we're going to do is our delta x, if we're going to keep it at 10, that's equal to our v naught x times this time of 1.549 seconds, right? The time of total flight. So if we get that, 1.549, we get a velocity in the x direction, v naught x, of 6.456 meters per second. So that's this component right here. And when we're looking at that, right, the problem is asking for the speed at which the mountain lion is jumping. And we generally give speeds with one magnitude. So what we need to do is we need to combine our x and our y components to make our hypotenuse. So we're just doing our Pythagorean theorem, right? The a squared plus b squared equals c squared. So we're looking for c, so I'm going to do 6, right? So solving for speed is with Pythagorean theorem. Right, so we're going to take our speed, velocity, I'm going to call it velocity because we are going to solve for the angle, is equal to the square root of 6.456 squared plus 7.774 squared. And what we get when we do that, our speed, 6.456 squared plus 7.774 squared equals square root. I get 10.1 meters per second. So this lion is launching with its velocity of 10.1 up and to the right for us. And so we plug that in. And then it's also going to ask for the angle. And remember, we can use the inverse of our functions to figure that out. So since I know the 2 legs, I can use tangent here. So speed, we use Pythagorean theorem. For the angle, we use SOHCAHTOA, or the inverses. Right, the inverse of tangent in this case. So remember, tangent of the angle is equal to the opposite over the adjacent. Okay, remember we're looking for this angle, that is blue theta, up in our picture right here. So our opposite, so if I'm looking for theta, it's going to be equal to, right, we do the inverse of the tangent because we divide by it, and then the opposite, in this case, is our y component, 7.774, divided by the adjacent, 6.456, and if we do that, 7.774 divided by 6.456, inverse of the tangent, we get 50.3 degrees, and you can be calling it 50.43 works, because remember, if we are talking about directionality, we assume that out this way along the x-axis is considered 0. So if I say 50.3, we are assuming we are going up from 50.3, because the way that we do angles, we go in a counterclockwise fashion from the x direction. If you want to be super duper specific, you can say north of east, right? Because we are going east, and then we are going 53 or 50.3 degrees north of that, so we call that northeast, however you want to talk about it. But we would say the velocity is 10.1 meters per second, 50.3 degrees